There we go. Yeah, we could format them so that we don't have all that nasty E stuff in there. E. But it seems wrong. Maybe not. Time spent working is 1. The total time in this one's 254. So this one took 2:00:244. That's weird because this thread didn't have any heavy items, but yet it took longer than any of these other guys. It's a little strange. Not gonna lie. But it could just be scheduling. Because I mean the time taken per chunk is so small. So maybe what we should do to eliminate that noise from our measurements is just to increase the size of each chunk by a lot. And then if the total size gets too big, we could just reduce the number of chunks. Don't save that. Okay. I think when we create the file, by default, it just writes over it. But if the amount that we're writing is less than the amount that was already existing there, the extra would just remain. Like, I think what we want to do is we want to open it in a mode where we're truncating it. So std IO open mode. That's not it. We truncate. Yeah, I want to truncate the file when I open it. I don't know what the default is. It might be truncate, but it might not be. We'll just truncate it. So yeah, we want our chunk size to be larger, like a lot larger. Let's make the chunk size 800. And we'll keep this and this the same. Let's increase the heavy probability to 5.5. Build. Should probably be running this in release as well. Yeah, let's just make it in release. Doesn't matter. We're not going to be stepping through. Build. And start without debugging. Okay. So that takes 0.1 seconds in release. It's not a terrible runtime, but we could even increase the chunk size if we wanted to. Now, I mean, why not increase the chunk size? Let's do it. We want to get rid of as much noise from our measurements as possible. So that'll be, what, 1 second? Seems like a goodish amount of time to run a test like this. And if we go into the folder, we open timings.csv. Yeah, whatever. What do we see? I mean, I would like, let me just change the formatting on. All right, so now we have it all with 6 places, which is annoying for these. But wait a minute, maybe I could just, yeah. Heavy. Could format those. General. Yeah. There we go. All right, so. So if we compare 2 of these together, one that has a lot of heavies against one that has not a lot of heavies on the same working thread, you can see that the one with more heavies does seem to take longer. So we don't have any weirdness in that situation. Chunk time, any given chunk is about, 10 milliseconds. So if we look at a particular row here, let me find one with a discrepancy maybe. I want to find one with a big difference between the number of the number of heavies. Not seeing. Let me do. I just gotta. I spy with my little eye. I'm looking at like somewhere like it has 120 maybe. I'm just not seeing it. This one has 77 versus 114. That's pretty good. So the one with 77 should have quite a bit of idle time. Let me see here. So that's this one. So this 77 is here. Its idle time is about 1 millisecond idle. This one has less than half a millisecond. This one has barely any idle time. The one that has the most heavy items should be the one with the least idle time, because it's the one that's going to be holding up the show, basically. And the rest of the guys, they're going to finish before it, so they're going to have idle time while they're waiting. All right. So now I think we have our setup here. Don't save that. All right. Now I would like to see, I would like to add one more column here. And the column will be the total idle time, but this isn't like, this is total idle time added over all the threads. So technically it could even be longer than the chunk time itself in a really bad situation. But we want to see how much time basically in total threads are wasting. Wasted thread seconds is what we're looking at. So total chunk time total idle, total heavy. So total idle, I mean, let's just make things a little cleaner here. Once auto total heavy is equal to this. And we'll do the same idea, but for total idle. So that's annoying. I don't have the idle time in here, so I can't just accumulate over it. God damn it. Now I'm very mildly annoyed. We loop here. So, I mean, yeah. Not that optimizing this is going to make our lives any easier, but float we can do yeah, we'll just clean this up a little bit, and this will be able to fit on one line then in my personal estimation. And then here we can do total idle plus an equal idle, total heavy plus an equal heavy. Yeah. And this is not a situation where we need to use accumulate then. So we won't use it. What's your problem? Yeah, size T. That's missing a capital H, and my copy paste has failed. There. Okay. So now we can do total chunk time, total idle, total heavy. There. Okay. So now we can see the total amount of time spent idling per chunk. Let's run it. And let's open this. Okay. And now we don't have the data because I messed something up. Total idle, total heavy. Okay, what did I mess up? Don't save. Probably I don't have enough of these boys in here. Need more. They should match. Doesn't give you an error though if they don't match. It's just like, you know, you gave me some extra, but that's fine. It's very chill code. Doesn't like to rock the boat. Yeah, so now we can see how much time has just been wasted by threads. And here we can see 3 milliseconds wasted by threads. Can we see more than 3? I think 3 is probably about the maximum. Oh, it's almost 4. And so in the place where we see 4 seconds being wasted by threads, we see, well, these two, yeah, are about 90, and then these two are about 100 and 10, 120-ish. So yeah, this one is not idling. Let me see here. Format cells, we'll do number 6. Yeah. Okay. Where were we again? Here? I think we were here, yeah? Yeah. So this one, I mean, this is kind of strange, right? Oh no, because so this one has fewer heavy items and it's spending, 1.4 milliseconds idling. That makes sense. This one has barely any idle time because it is the weakest link. It's got the most heavies. This one though, even though it only has just a few fewer. No wait, I keep getting mixed up which one is which. Yeah, this one is not spending a ton of time idling. It's spending a decent amount though. This one's spending quite a bit, yeah. But we can see, like, when there's a fairly big discrepancy between the largest and the smallest, you're going to get more idle time. I'm sure I could do some, like, Excel magic on this to find me, like, the maximum and the minimum, but I don't feel like it. This is good enough for me. So yeah. Anyways, let's look at our goals here. Yeah, we got that, we got all this stuff. And I think we are about ready. I mean, the last thing we want to do is control the distribution of the heavies. So what would happen if we got the worst case scenario? So we could create a generation function. Let's call this one generate datasets random. Where is it? There. There we go. So what if we created another function and we used it to to compare two scenarios. So both scenarios, every chunk will have the exact same amount of heavies. In one scenario, the heavies will be equally distributed throughout the container. So every worker will get about the same number of heavies. In the other situation, all the heavies will be concentrated at the beginning. They won't be distributed. And so because we just split the chunk into 4 contiguous sections and give each section to a thread, if we load all the heavies at like the beginning of the chunk, one thread is going to get, basically all the heavies, and then the others are going to get all light. And then we can see how bad, like the data sets are going to be, pretty much the same amount of heavies per chunk. So the workload is technically the same workload. But if we distribute the heavies in different ways, we can see how that affects our total runtime. That's what I'm getting at. I'm just noticing right now, this shouldn't be data sets, it should be data set, right? Or it should be generate chunks, I guess, but whatever. Data set is a vector of chunks. Now I changed the name of it. Why is this? Yeah, there we go. That should be an error. There we go. Okay. So generate data set. Let's call this one even, which for even, generate data set evenly. So this will evenly distribute the heavies across the data set. So and we'll just use the probability heavy as the percentage of the, chunk size. Multiply this by this, and that'll get us the number of heavies. So that means that we just go 1 divided by this number, and that will tell us every nth item has to be a heavy, right? Because if I do 1 divided by 0.5, that'll be 20. Every 20th item should be a heavy. Yeah, that makes sense. So, distribute it evenly. So we don't need the Bernoulli distribution. This is going to be mutable because, to make it mutable, we have to do this. Because we need to keep track of our count. I'll just do like I is equal to 0. Mutable. Yeah, okay. Our distribution. So heavy is equal to that's not how you do that. Const auto is heavy is equal to, what's your goddamn problem? Whatever, we'll figure it out. Is equal to let's make a, trying to think. This is probably an int. Yeah, that's an int. So let's do int every nth. That's const. Is equal to probability. Probability heavy. So 1 and this should be int. So we'll make this auto then. Okay. All right. Every nth. And then is heavy is equal to I is equal to every nth. We'll post increment that. We could just do that here then. Just make it a one-liner. There you go. Increment I, compare that to every nth. And no. It's not how you do this. It doesn't make any sense. Mod every nth is equal to 0. Let's do it like this then. All right. So now our data set should have equally distributed heavy boys. Random just data. Yeah. So let's try it out. Let's just try it out. We'll take a look at it in the debugger. Why are you taking so long to switch configurations? Evenly. We'll put a little boy there. Let's compile that. Please don't give me any guff. Thank you. Bam. Take a look at chunks. Take a look at chunk 0. And true. False, 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 false. Where's the 20th one? True. Where's the 40th one? True. There you go. Okay. Okay. Like that. And the other version of this it's probably a better way than just, copy pasting these functions, make it kind of parameterized, but I don't care. Don't care. Didn't ask. Generate data set stacked. Total heavy, total number of heavies is equal to chunk size times heavy probability. So this should be a double. And then that should all be converted to an int. So that's the total number of heavies. And we can, I is equal to 0, is heavy, I plus plus is less than total heavy. There you go. And that should stack all the heavies at the beginning of the chunk. Right? Makes sense. Stacked. There. All right, step over that. Take a look at the chunks. Take a look at chunk 0. And we can see lots of trues. At the very beginning here. 100 trues. Oh, I thought I saw false. Then we get the falses. Where did the falses come in? Wait, how many? Okay, so there's 8,000. And the break point is about here, right? 399, 400. Seems about right. Maybe? 4 times 20. Yeah. Yeah. 400 times 20 is 8,000. There you go. Okay, so there's your boy. Now we can generate our stacked data set. We can generate our even data set now. So let's just test this out. Do a release build. So with these data sets stacked, and again, I just want to iterate, stacked and even, they are the exact same workloads. It's just how the items are distributed to each of the worker threads is the only issue. So if I run the evenly version, takes about 1 second. Now let's run the stacked version. Gotta recompile it. It's taken 1.7 seconds. So not quite twice as slow, but 75% slower. That's a pretty big difference considering we didn't change like the data. The workload is the same workload. We just distributed it differently and we got quite a bit different results. And I mean, if we make more heavies, that's just going to make the problem worse. So if we put like 15% of the workload now is heavy, and let's make this a little nicer. What do we have here? We have argv, argc, and argv. So go if stacked, return this, else return a little cursed. I can't give up my freaking braces. Just doesn't feel right. There we go. That's better. All right. So we generate our chunks based on this, and we go into here, and we do if. So wait. Argc is greater than 1, and let's go using namespace std string literals. So if argc is equal to 1 and argv at 1 is greater than 1, and argv at 1, which is the first parameter, is equal to stacked. Stacked is equal to true. Do experiment stacked. There we go. Now, command line arguments. We have no command line arguments here. So if we run it, it's going to run without being stacked. It's going to take longer than 1 second because we tripled the amount of heavies. It takes 1.63. Still less time than the original with the stacked. Now if we add the parameter stacked to the command line, run it again. Wait a minute. Is that even working? Oh, wait. I gotta make it a string. That was just a... Yeah, so if you compare a C string to another C string, it's just gonna compare their addresses, which are, you know, usually gonna be different. We wanna actually do a character by character comparison, so we gotta make a smart string, not a dumbass string, like that dumbass string like that one. Anyways. So we, again, not stacked. Should be 1.6-ish. 1.65 with stacking. 3.9 seconds. So over double, maybe 2.5 times slower, something in that ballpark. Definitely not a good scene. And it just gets worse if you make the heavy iterations. Like, they're only 10 times worse than the light. But if these guys were like, this was like 10,000, the story would just get worse. And remember, it's between stacked and not stacked, exact same workload. Exact same numbers in there. In fact, let's just do a little test. My prediction is that the results should be the same whether you run it stacked or unstacked. The order in which you do them shouldn't matter. So it's 1564. And if we run it stacked, don't make a liar out of me. Come on. God damn it. Let me think here. Oh, okay, so the random generator is going to be different because, let me think here. Is it going to be different? It's the same number of guys. Yeah, but which items end up being heavy? That's the difference. Okay. So if I want, this is actually pretty important. If I want the results to be the same, I have to make sure that the same items in the sequence, like the same values, are heavy across both of these. I can move those around in the container, but the ones that are marked as heavy have to be the same value. Does that make any sense? It's mildly complicated, but it's not that hard. So now the question is, okay, so but I do want these data sets to evaluate, these different data sets to evaluate the same value, because I want to be able to, you know, validate my approaches in the future. So that means that if I want to stack them, okay, so what I'm going to do, this is going to do some C++ stuff. Oh. Mouse pointer is getting crazy. Okay, so we'll use this as the baseline, generate data set evenly. Now, if we want to generate data sets stacked, what we're going to do is we're going to do auto data is equal to generate data set evenly. And then we're going to do std ranges partition. We're going to partition the container to put all the heavies in the beginning. I can't remember how that's going to work, but it's going to be one of two things. So I'll just try one. So that would be data. I'm going to partition data. Predicate would just be... That's a good question. Does it have a default predicate? Can I just give it a default? And then the projection is going to be task heavy. Okay, so It doesn't have a default. I want a default that just passes through. And I could just do that with a lambda, but I feel like there is something in functional that can just do that for me. So std functional, not std function, standard header library functional CPP reference. Mem function plus minus divides and negate equal to less than no. Logical not. So I want not the not. I want the not of the not. Identity. Identity. Yes. That's what I want. Is that struct identity? Class T. So std identity task. How about bool? Maybe it doesn't exist. Let's include functional. Why does identity may not have a template tag? Because the template is on the operator, not on the... Okay. Still doesn't like it, though. Okay, yeah, because this is a vector. Okay. I have to partition each... I have to partition each motherfucking chunk in the data individually. So I should do it like this. I should partition the chunk by its heavy member. So I'm going to project into the heavy member and just use that Boolean directly to partition the chunk. I might have to put it as not. I can't remember how it's going to work, but let's just try it out. So generate data set stacked. We got them set there. So now we go down here to here, 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 run. Okay. It's taking quite a time to partition the large data sets, I think. Or did I not push the button? Okay. Well, I should just press here and go start. Okay, it didn't take quite a time. I just didn't press the button, which is good. Things taking a very long time is usually not a good sign. Here. Okay, so now the heavy is true, is at the beginning. I got to scroll down to 400. 400 here. True, true, true. Wait a minute. Because I changed the percentage to higher, 15%. So it should be at 1200 is where the breakpoint should be. So if I go to 1200. Okay, well, you're making a freaking liar out of me. Where's the breakpoint? False. Here. Seems suspicious. 1334, 1333. .15, which is 8. It should be 1200, right? Am I crazy? Am I taking the crazy sauce? I mean, the partitioning seemed to have worked, right? These are all false. These are all true. But the number of trues are not what I would expect them to be. I mean, to be fair, I've only done this test of like the breaking point. I only did that test with generate datasets stacked, not evenly. Now, here's the thing with evenly. It uses modulus, right? So there is a little bit of floating point error, basically, because I'm not accumulating fractional parts. So I believe that this is just the my rounding error, not floating point error, rounding error. This is what my rounding errors is, which is good because now we can see that the evenly and the stacked datasets, they weren't actually exactly equal datasets. Like they weren't the exact same weight because stacked or evenly had a few more, maybe like 10% more work. Yeah, it looks like about 10% error there, which makes sense. It's rounding error basically. Okay, that makes sense. But because we're generating now only with this one, and then this one just takes that one and partitions it, now they're guaranteed to have the same amount of heavy in either. Interesting. Okay, well, that's good to know. If we would have looked at our CSV files and looked at the heavy counts for the stacked and non-stacked versions, we could have verified that, but I didn't look at those. I was just looking at the runtimes. Okay. So now, build. Now we should be able to verify that they both come out to the same result. Let's try this. So the non-stacked version, 1564, which should be the same as before, I believe. We didn't change it. 1564, and now this should be 1564. Don't make a liar out of me. I'll be very disappointed. 1564. There you have it. Okay. So now we have equivalent data sets. They are both the same difficulty. It's just that there's a different distribution of hard work items and easy work items. And that distribution is going to manifest. If we do the worst case, where all the hard items are given to a single unlucky worker, wait a minute. Why are you... Did I not... Something's wrong. Let's try it again. It might not have been able to write the CSV because it was open in Excel. So we're going to try that again because those numbers did not look right. Right? All the heavies should have been stacked onto one of the worker threads. Please be... Yeah, here we go. Okay, there we go. So we see that worker 0 has all the heavies and all these other workers have nothing. And we can see that they're spending, like close to 40 total. Oh, that's total idle. Yeah. So close to 40 milliseconds. They're just sitting around with their thumb up their butt. And this guy almost never has any idle time because he's got all the work. He's got all the heavies, man. He's got the shitty end of the stick every single time. He's mad and he ain't going to take it anymore. So yeah, we're wasting 100 milliseconds every chunk. And like the total work time, the chunk work time is only 40 milliseconds, and yet we've managed to waste 100 milliseconds per chunk of thread time, and that's because we don't have an equal distribution of our heavies. But like I said at the very beginning of this whole thing, with actual real life data and processing, we can't tell which are heavies and which are light. And so we could distribute them equally among workers. We can't always tell that. Sometimes you just don't know. And so you have to roll the dice. And if you roll the dice and all the heavies get stacked onto one worker, you're going to have a very bad time. So we need to figure out how we're going to keep our workers busy in this situation. And we're going to have to redo the way we distribute our work. But that is going to be, we're going to do that in another video. But yeah, this preparation, this is pretty much all the prep that I am going to need to do a video. So I'm going to do one video, and that's just going to be creating this test code and demonstrating the problem of an uneven workload. That'll be one video. So this is the prep work for a single video. And yeah, when you see more prep videos, those are now going to be on creating the solution to this problem that I've presented. But that'll be another time, another day. You know, leave your comments. Let me know. Hit the like button if you like these in-depth videos. Very laid back, chill, long form. I don't anticipate that a lot of people will actually be watching these, but we'll see. We'll do this. We'll do this experiment for a little while. We'll see where the dice fall. Until then, thanks for watching, and I'll see you later with some more C++ multithreading.